Correlation versus causality. The third variable problem. In any correlation, causality between two variables cannot be assumed because there may be other measured or unmeasured variables affecting the results. The direction of causality. Correlation coefficients say nothing about which variable causes the other to change. However, the correlation is not necessary for any argument that the two variables are causally related. Do not ascribe more meaning, for example, causation, to correlational coefficients than they deserve, although it is a powerful tool to examine associations. So correlation is an important analysis for further advanced analysis. For example, regression factor analysis, PCA. Pearson's are critical values for a two-tailed t-test. The coefficient of determination, r squared. How much of the variance in the scores of one variable can be understood or explained by the scores of a second variable? When two variables are correlated with each other, they share a certain percent of their variance. For example, height and weight. The correlation coefficient squared is called the coefficient of determination, the proportion of the variance that x and y share, the proportion of y's variance that is related to x, the proportion of y's variance that is accounted for by x, the proportion of y's variance that is explained by x. Examples: if r equals 0.1, then 1% of the variance is shared, or 0.01. If r equals 0.8, then 64% of the variance is shared, because 0.8 squared is 0.64. What is a sample linear regression? A way of predicting the value of one variable from another. It is a hypothetical model of the relationship between two variables. The model used is a linear one. Therefore, we describe the relationship using the equation for a straight line. What are the two variables? The predictor versus the outcome variable. Describing a straight line. We have the regression coefficient for the predictor variable, the gradient of the regression line, and the direction and the strength of the relationship. There's also the intercept for the value of y when x equals 0, and the point at which the regression line crosses the y-axis. For the first formula, b equals Pearson's r. The yellow highlighted formula is the unstandardized version of b, while the formula in the green is the standardized. Just like correlation, we have covariance with the two variables, and the Pearson's r correlation coefficient. Intercepts and gradients. Which one shows the slope with different intercepts? Which one shows the same intercept but with different slopes? How good is the model? The regression line is only a model based on the data. This model might not reflect reality. We need some way of testing how well the model fits the observed data. The method of the least squares. How to fit the line. The regression model. Line. Blue circles equal the observed data. Green dots on the line equal the predicted values. For a perfect fit of the data, the model should predict the same value of the outcome as was actually observed. The green dots should equal the blue dots. As you can see, there are errors in the predicted values, sometimes overestimates, sometimes underestimates. The total variability is the variability between the scores and the mean. The residual error variability is the variability between the regression model and the actual data. The model variability is the difference in variability between the model and the mean. Why using a mean model is particularly bad? It does not change when the predictor changes. The slope of the gradient is 0, which equals the mean. Partitioning the sum of squares. So you have the sum of squares total, the sum of squares model, and the sum of squares residual. The model is the green area, and the residual is the red area. The residuals are the difference between what the model predicts and the observed data. The sum of square total represents how good the mean is as a model of the observed data, the most basic model.